Chapter 2, Lecture 5, Heat Generation in a Solid. In this particular lecture, we're going to take a look at uh, a solid object that's either a wall or a sphere or a cylinder that has heat being generated inside of it, and we'll look at developing the equations. Many practical heat transfer applications involve the conversion of some form of energy into thermal energy in the medium. Such mediums are said to involve internal heat generation, which manifests itself in a rise in temperature throughout the medium. Some examples of this are resistance heating in wires. So if you run current through a wire, as shown here, the current itself can generate heat, as we know, because you have the power of the current, which is I squared times R. And that heat is generated throughout the wire and then conducts itself to the surface. You also have chemical reactions inside of a chamber, inside of a solid. Another example is nuclear reactions inside of a fuel rod. So let's come up with a formula for how much heat is generated inside of a solid. So here we have a solid. It has a certain volume. It has a certain thermal conductivity. And so inside, we're going to generate heat, and that heat is given by Q dot, which is equal to the energy generation within the solid, E dot gen. That heat then is conducted to the surface, and at the surface, it's going to convect to the outside. So at the surface, it has a temperature T sub S, and far away from the solid itself, it's going to be, we call it T infinity. That's just the temperature far away. So we know what the formula for Q dot is E dot gen times the volume. And then the Q dot is H times the area times the difference in temperature from the surface to the infinity. So this one takes care of the Q dot once it gets from the surface out into the away from the solid. This is what's generated inside the solid. So if you take this equation here and you set it equal to set these equal, they have to be equal in steady state operation. You can solve this for T sub S, and you come up with the equation here. So this is your basic equation, but you can apply this in different situations. For example, if you have a plain wall that has a thickness of 2L, then the area of the surface is 2 times the area of the wall, and the volume is this 2L times the area. You can substitute this in and solve this equation specifically, substituting for V, substituting for A sub S, and so you end up with this equation here for a large plane wall. And similarly, you can do the same thing for a long solid cylinder. The area is simply 2 pi r, and the volume is given by the equation here, substituted in this equation, and you end up with the temperature from a cylinder. And similarly, you can do the same thing for a sphere. So let's look at how this works. So the maximum temperature. So inside this wall, we're generating heat. So the maximum temperature is going to occur at the very center. And so the book works out the formula, but it's simply E dot gen times L squared over 2K for the delta T max. So delta T max is simply T0, which is T max minus T sub S. That's the delta T max. So here, this is kind of a symmetry kind of situation when you have, here's the wall itself, and on either side you have the same temperature T sub S. And far away from the wall, it's T infinity on both sides. This is symmetric. The maximum temperature is going to be right in the center. You can also work this out for a sphere and for a cylinder, and you end up with similar kind of equations. So let's go back to what we studied in the previous sections of the textbook. We looked at the equation for three-dimensional, the general equation, three-dimensional heat transfer, where you have E dot gen that's generated inside the wall. So let's work this out for special kind of situation. Let's look at a large plane wall of thickness 2L. So here's the center of the wall, and it's L on each side. So the whole thickness is 2L. You got a temperature on one side called T1, a temperature on the other side T2. So, this is the one-dimensional problem. So we can get rid of this term here. The temperature is only going to be a function of x. It's one-dimensional. So this cancels, and the temperature is it's steady state. So here, this is going to be equal to 0. So when you solve this, of course, this is one-dimensional. So the k can come out, and then you end up with a double derivative with respect to temperature, with respect to x squared, divided through both sides by k, and so you end up with this equation here. So this is pretty easy to solve. We simply need to take a couple of integrals and solve this right away. So if we take the previous equation, we integrate twice. We end up with this general equation here where we have two unknown constants, C1 and C2. So how do we determine C1 and 2? Well, we have to have some boundary conditions. So let's work out the case where T1 is greater than T2. So here, if you plug in a value for for L, T at minus L is equal to T1. You end up with this equation, and T at x equal L here is equal to T2. So you have two unknowns. You got T1 and T2, and I'm sorry, T1 and T2 are known. The only unknowns here are C1 and C2. So you got two equations, two unknowns. You can solve for C1 and you can solve for C2. So here you can take these two and plug back in for C1 and C2, and then write a more general equation. So here's our equation, and we solve for C1 and C2, so we can plug these back in, and then we can simplify down into a final equation that looks like this here. So for part B, we want to find temperature when T1 equals T2. So if T1 equals 2, then this cancels, and these were equal, so it becomes 2 times T1 over 2, so that 2's cancel. You're just left with T1, and you got this first term here. Okay, that's the end of this lectures for chapter 2.